Okay, thank you. Yes, so as Brajesh said, I'm going to present something that I think is very, very significant. And this is something that we've been working on for about 4 years in secrecy so some of you have been aware of it, have been at least aware that something like this is going on within AWS. Byron has also been dropping vague hints in public talks, that something like this is happening. But now this is only really the second public talk that's been given on this so far. So this is very, very new. And although I'm here presenting it, of course, this is kind of the product of a big team effort. So some people familiar to this community as well have also been working on this, including Nathan Chong and maybe Robert Dawkins, you might be aware of kind of the comps at work. So I am going to talk today about the Nitro Isolation Engine. So this was announced at AWS reInvent back in December in Las Vegas, alongside Graviton5, which is kind of the next generation of the kind of the AWS ARM-based processors that are imminently going to go GA. So the Nitro Isolation Engine will go GA with Graviton5 as well. So the context of this talk is AWS EC2. So if you're not familiar with EC2, it's Elastic Cloud Compute. So the idea is that there's a kind of a cloud console, an API that you can kind of programmatically launch virtual machines using. So the general idea is that you configure a virtual machine, you decide how many processors the machine has, how much RAM, what operating system it will be loaded with. And you click launch, and a few minutes later, you will get a kind of a message saying, here's an IP address. You can SSH into this machine now, and it's yours. Okay. So what makes this business model work is the idea that actually mutually distrusting workloads from different customers are co-tenanted on the same physical machine. So this is kind of the economics of it. This is what makes it cheap. You basically have potentially dozens, if not hundreds, of customers on the same physical machine. Okay. So one question that we often get asked as a business is, well, given that, how is my data actually protected by EC2 when one of these kind of shared machines is operating? We have some pretty good answers to that. So we have published detailed white papers on the design of the Nitro system. So Nitro is kind of the generic product name for kind of the virtualization software that powers EC2, or at least most EC2 instances. We've also invited in kind of external auditors like the NCC group, who are based in the UK, I think, and maybe there's somebody here from the NCC group, and they've come in and kind of audited our claims, and they've written their own kind of reports. But still, there's at least a class of customer that isn't satisfied with this, and also within AWS, there's always kind of a push to improve our kind of security, our security posture, our transparency, and so on. So essentially what we asked about 4 years ago is how can we provide even higher levels of assurance about the protection of our customer data when it's in use? So before I kind of get into answering how exactly we've done that, it's worth just stepping back a little bit and thinking or discovering how EC2 actually works today, at least in kind of abstract terms. So this diagram is specific to ARM. So on the left-hand side, you've got EL0, EL1, EL2. So these are the exception levels that are kind of familiar, if you're familiar with ARM. They're essentially akin to privilege rings on x86. And the general idea is that EL0 is the least privileged kind of exception level. It's where your user space software, things like your Outlook, email client, your word processor, and so on. Those sorts of kind of user space applications execute at EL0. And gradually, you build up kind of levels of privilege. So EL1 is where a typical operating system kernel, like the Linux kernel or the FreeBSD kernel or the Windows kernel would be executing out of. And EL2 is an even higher level of privilege. And this is where the hypervisor executes out of. So if you're not familiar with the term hypervisor, you can think of it as a little bit like an operating system for operating systems. So the general idea is that an operating system virtualizes a physical machine. So each program sees a view of the physical machine, like your Outlook kind of email client. Doesn't need to know what other programs are loaded into memory. There was a virtual view of memory that is provided to it by the operating system. The operating system also kind of mediates the interface between the hardware and the user space applications by providing kind of potentially a virtualized interface for those. And a similar process is happening at the kind of this next level of up. So hypervisor is virtualizing the virtualizer. And so today that task is done by the AWS Nitro hypervisor. And essentially what the hypervisor has to do, its kind of key task, is to keep all of the guest virtual machine instances that are running on this physical machine separate from each other. So each virtual machine instance is a full operating system, a full Linux with its own user space, and it needs to think that it's got access to the entire machine exclusively. So there can be no leakage of information between different virtual machine instances, which would constitute a security breach. And there can be no leakage out as well of a guest virtual machine instance to the Nitro hypervisor, at least not without reason. I'll get onto that later. So if I skip past this. Okay, so if we step back and look at the Nitro hypervisor, how it's organized internally, we can see that actually this kind of core task of separating the guest virtual machine instances from each other is actually performed by a small portion of the total code that's involved in the Nitro hypervisor's implementation. And conceptually, you can think of splitting this out. And realistically, what that code is the management of the page tables. So as I said before, the operating system itself is presenting a virtual kind of view of memory to a user space application. And the key hardware enablement technology that kind of allows this is the page table, which is essentially a hierarchical data structure in memory that provides almost kind of like a function from virtual addresses to physical addresses. Okay. Now, what the hypervisor is doing is managing a second stage of page tables, the stage 2 page tables in ARM's kind of parlance, which actually then kind of provides another map, this time from intermediate physical addresses to physical addresses. And therefore, the stage 1 virtual machine kind of page tables under their management are actually managing or implementing a function from virtual addresses to intermediate physical addresses. So if you compose the two things together, then you have a kind of a composed function that still maps you from virtual addresses to physical addresses. Apart from the first kind of part of this composition is under the management of the virtual machines themselves. And the second part is under the management of the Nitro hypervisor, or this minimal TCB. Okay. Now, once we've identified this minimal TCB, what we can do is conceptually deprivilege the Nitro hypervisor, or the remainder of the Nitro hypervisor that isn't associated with kind of like the management of on the separation of the virtual machines. So we push that back down so that it's no longer in a position of relative privilege compared to the guest virtual machines. And the only thing that is in that privileged position now is this minimal TCB component. And with this repositioning, re-architecting of Nitro, what we've done is we've performed a classic policy and mechanism split. Okay, so all of the policy, all of the business kind of rules and so on about what gets scheduled, what resources are assigned to virtual machines, and so on and so forth, that is retained by the Nitro hypervisor, which also retains its role of communicating with the AWS control plane and kind of interpreting signals that's coming from the control plane. But in its place, kind of this minimal TCB has retained all of the mechanism, all of the components of the old hypervisor necessary to separate, and it is now going to expose an interface to the old Nitro hypervisor through which guest virtual machines will be managed. And in fact, that will be the only way that the Nitro hypervisor will be able to interact with the virtual machines through this interface. With this minimal TCB component will act a little bit like a monitor. So it will be able to see what the Nitro hypervisor is trying to do to virtual machines and the secret data, our customers' data within them, and intercede or stop bad behaviors. Okay. Now, this minimal TCB is what we call the Nitro Isolation Engine. So in kind of terms that I think Kathleen used in the first talk, this is essentially a separation engine, separation kernel. It is conceptually similar to SEL4 in that respect. So it is very, very minimal. So we're talking on the order of tens of thousands of lines of code. And this is compared to the Nitro hypervisor implementation, which is kind of hundreds of thousands, maybe even millions of lines of code. So with this split, what we have now is not only a code base that is much easier to audit by hand, but also a code base that is possible to verify. And in fact, from the very first line of code that was written for the Nitro Isolation Engine implementation, the idea has always been to verify it, and the automated reasoning group have been involved from the very first line of code. So we have made sure that it is verifiable as well by influencing the design and the engineering process. Okay. So to say a little bit more about how the Nitro Isolation Engine works and what it exposes to the rest of the Nitro system, just in very abstract terms to be able to understand the rest of the talk. Essentially what is being exposed is a pair of hypercall interfaces. So you might be familiar in a standard operating system, if you want to open a file, say from like a console program or Outlook or another user-based process, you have to issue a system call. The system call basically switches into the kernel. It performs a context switch and asks the kernel, please open this file for me, at least in most kind of commodity operating systems. And the kernel will do something, it will have some effect on the system, or it may be say, no, actually, no, that's not allowed for some particular reason. And then it will switch back to kind of the user space context. And if it's successful, it will give you something like a file handle or whatever. So a hypercall interface is the same again. Apart from this time, the jump is going directly to the hypervisor, to the Nitro Isolation Engine. And it will do something on behalf of either a guest virtual machine instance or on behalf of the Nitro hypervisor. And of the two interfaces, by far the most interesting is this host facing the kind of the Nitro hypervisor interface. In fact, there's barely any kind of interface at all that's guest facing. So I've focused on hypercalls here, and you can think of these as a bit like a synchronous kind of interrupt or abort in ARM terms. But also there's other types of aborts or exceptions or interrupts that we also have to handle as well. So things like instruction aborts and data aborts, these all got handled by the Nitro Isolation Engine. Also asynchronous kind of interrupts of some hardware interrupts or an S error in ARM's terms, which is kind of indication that there's something gone catastrophically wrong with the hardware. We also have to handle those as well. So in general terms, what the Nitro Isolation Engine is doing is kind of managing a series of state machines. So the most interesting state machine, and the one that we focused on initially with the verification work, is the state machine associated with the virtual machine itself. So the kind of the customer virtual machines that I was talking about on the previous slides. And you can imagine that there's kind of a staged process through which the Nitro hypervisor sets up or creates a new virtual machine in preparation for it to be executed. So from ab initio, you call a particular hypercall vm.new vmid, and this will give the hypervisor back a handle that it can use to kind of refer to this husk of a virtual machine that it's just created. Gradually, it will then map in pages of memory from its own address space and perform other kind of initialization tasks, like setting the initial registers of kind of the virtual CPUs associated with that virtual machine. And then eventually we'll call this vm.finalize hypercall, which flips the kind of the newly created primitive virtual machine into an executable state. And once it's in an executable state, you can then, if you're the Nitro hypervisor, call vm.vcpu run, which allows you to execute a kind of a virtual CPU and do some sort of task And then there's kind of another teardown kind of component where you gradually, once you've finished executing and the customer's done with the virtual machine, you gradually release resources, unmapping data and passing it back to the Nitro hypervisor, and then eventually just destroying the virtual machine and freeing the vmid. Okay, so this is the kind of the core life cycle associated with the Nitro Isolation Engine. This is actually what you see on the screen is probably estimating about where 90+% of actual execution time is spent when actually running on a system with the Nitro Isolation Engine. So 90% of the Nitro Isolation Engine's execution time. And this is why we've focused on this. This is by far the most important part to get right. Okay, so switching now to the verification task. So if you want a too long didn't read, you want to go to sleep for the rest of the talk, this slide is effectively what you need to remember. So for every function in the implementation of the Nitro Isolation Engine, we are going to write pre and post condition specifications for those functions. To be able to pull this verification task off, we're going to also restrict the fragment of Rust that we're using in the Nitro Isolation Engine. And because we work closely with EC2, the engineering team, we're essentially side by side in the office. We can influence them. They are happy to kind of restrict to a kind of a very vanilla fragment of Rust. We then model the semantics of Rust in Isabelle whole. So we use Isabelle as the kind of theorem prover of choice. And then we translate all of the functions from Rust into this embedding of Rust in Isabelle that we call micro-Rust. And then we prove properties of this formal model of the Nitro Isolation Engine. In particular, we are going to prove two major classes of property. One is functional correctness. So we're going to use the pre and post conditions, the specifications that I talked about at the top, to prove that the implementation always matches that specification, and it does what we think it does. And the second class of property are security properties. So we're going to also prove confidentiality and integrity for guest virtual machine data. So, of course, we could charge off and just do a ton of kind of verification work that's completely disconnected to like the empirical reality of what's executing on a Graviton machine. So to ground this verification process, we also use a process of conformance testing, where we test the real Nitro Isolation Engine against our formal models of Isabelle, using Isabelle's code generation to get essentially a second version of the Nitro Isolation Engine, and run them on traces to make sure that they always stay in lockstep, and therefore that our models are kind of actually realistic. And as a result of this, we find bugs and design issues, and we find them quite early. And some of the bugs are very, very interesting. They're not things that reasonably you would be able to find just using testing, at least not without knowing that that bug is there. It's generally kind of beyond testing. And I should say also that all of this verification work is on top of the kind of the standard engineering process that AWS already uses. So it's not in addition. It's not replacing testing and kind of like code review and so on. We're doing this strictly as a value add. To say quickly, kind of just give in general terms the strategy that we're pursuing in the proof. Rather prosaically, the proof starts out with a series of TOML files. And the TOML files we call the machine readable specification. And what we need, because there's different teams associated with the Nitro Isolation Engine and its implementation, we all need to agree on a ground truth kind of specification. What is this thing even supposed to do? So in one sense, the MRS captures this idea. It describes all the different error codes that a hypercall can return if it's invoked in an erroneous state. It also describes in general terms what the expected effect in a success state the hypercall will have. So these are not written in kind of formal mathematics. They're written in a kind of a stylized English language that is easy for the automated reasoning team to translate into separation logic, but is also understandable by the EC2 team, and it allows us to kind of come to a consensus. The other role of the MRS is as a source of code generation. So about 40% of the Nitro Isolation Engine's source code by line count is auto-generated from these TOML files. So any important constant that needs to be shared between the verification and the implementation is all kind of embedded in these TOML files and auto-generated into Rust and Isabelle. Similarly with common types and so on and so forth. Another important part of code generation is also the system register layout. So ARM has hundreds of system registers that control the functioning of the machine. The layout of these system registers is very, very complicated. So for kind of a typical system register, you're talking about 3 bits may control like some aspect of power management on the physical machine, and you need to get that right. So we take the official ARM XML description of these system registers and their layout, and we translate them into the TOML file, and then we use a utility MRS generator that performs this code generation and spits out Rust and Isabelle code from those. So once we've got the TOML files, as I said, we use the MRS generator. That will give us a sizable amount of Rust code. But of course, that's not all of the Nitro Isolation Engine implementation. That has to be augmented with handwritten Rust, which is largely supplied by EC2, the engineering team. It will also give us a substantial body of micro-Rust source code in Isabelle whole. But we also need to augment that by translating the actual implementation of the NIE into micro-Rust, and then also augment it further with kind of more handwritten Isabelle that actually provides the proof and so on. And that's largely the ARG's responsibility. So, as I said, to be able to pull this process off, we have to restrict the fragment of Rust, and largely this involves bounding all loops. So things like recursion is just not permitted. All loops also have to be naturally bounded, which is actually not unreasonable in an operating system like Nitro Isolation Engine. Almost everything that you're working on is naturally bounded. Certain pattern matching kind of forms are prohibited, but that is weakening actually gradually. Locking patterns are restricted, and trait uses and so on is restricted. Okay, so to give an idea of how micro-Rust actually looks, here on the left-hand side is the part of the original. It's part of the Nitro Isolation Engine implementation. That's real Rust source. So that I think is one of the maybe the implementation of the vm.map hypercall. And on the right-hand side is the micro-Rust translation in Isabelle. And you can see there's some minor syntactic differences that have been imposed on us by Isabelle's parser. So for instance, the comment syntax is slightly different. But if you put the two things side by side, the control flow is identical in both cases. You can clearly see that is an accurate rendering of the left-hand side. And that is what we're going for. We want what we call eyeball closeness. We want to be able to show the right-hand side to one of our EC2 engineering colleagues who know nothing about Isabelle, and tell them, yes, this is what we verified. Do you recognize this? Is this what you actually wrote? And they can certify that actually, yeah, we verified what we think we verified. Now from that, we then, as I said, provide pre and post condition specifications for all hypercalls and also data aborts, instruction aborts, asynchronous interrupts, S-error handlers, and so on and so forth. And we provide this using separation logic. And as this community is probably well aware, this allows us to kind of zoom in on the footprint, do local reasoning on the implementation of the hypercall handler, for instance. We can really zoom in. We don't have to consider all like aspects of the rest of the machine. We can just talk about what's actually going to change and what's required. And we use this custom separation logic library that we have developed. This is paired with a very powerful tactic for working with separation logic called crush, which basically makes this process tractable. This proof would just not be feasible without this kind of crush tactic. We kind of also transform the micro-Rust before we do this proof into, I've put SSA here, but it's actually a normal form, I think. It's essentially kind of a semantics preserving transform where common sub-expressions and things like that are hoisted out. That just simplifies things a little bit. And then we perform total correctness style proofs using a WP calculus. We prove for each hypercall that if it's executed in a machine state and with a set of arguments that correspond to one of the error preconditions captured in the machine readable specification, then that hypercall implementation will return the appropriate error call that's specified in the machine readable specification, and nothing else will change. So there's kind of like a transactionality property at play here. So if you're in an error situation, basically there's no effect on the system. But if all error checks pass, then indeed the hypercall implementation will have the expected effect on the system state that is captured by the machine readable specification. Now, naturally, as a side effect, because we're using total reasoning, total correctness reasoning, we get a series of corollaries as essentially a side effect of the proof. One of which is memory safety. So all kind of array accesses are bounded. They are within bounds where there's not going to be any type of runtime panic or unwrap, for instance, in Rust that gets triggered. They also terminate, which is kind of in part driven by the restriction on looping kind of bounds. So we get a series of other kind of nice behavioral properties as a result of our reasoning as well. To give an idea of what these specifications, these pre and post condition specifications look like, I don't seriously expect you to kind of understand this, but this is kind of one of the specifications of the PSCI CPU on hypercall. So PSCI, if you're not familiar with it, it's a power management kind of standard that ARM publishes. And essentially what's going on here is this hypercall is used by one of the guest virtual machines during boot. So it has a virtual CPU, the boot CPU running, and now it needs to boot up or power up its other CPUs during the boot process. And this specification corresponds to an erroneous condition where the vCPU that's already executing is trying to turn itself on. So it must already be on by the fact that it's executing. And therefore, we're going to return this already on error code. You can see the res line. We've got this already on. I mean, the effect that I'm trying to get at here with putting this up on the screen is how detailed the models are. So this is not kind of trivial verification. This is really quite detailed reasoning about the behavior of the machine, about the behavior of the Nitro Isolation Engine. Okay, so, how much longer have I got there? All right, I'm going to zoom through this then. Okay, so one of the other properties that we care about, aside from functional correctness, is what we call isolation. So you can think of this as the confluence of confidentiality and integrity. So confidentiality is the kind of inadvertent flow or the illegal flow of information out of a guest virtual machine, either to another virtual machine or to the Nitro Isolation Engine, to the Nitro hypervisor itself that's unpermitted. Conversely, integrity is the inadvertent or illegal flow of information into a guest virtual machine so that you could potentially influence its behavior in an untoward manner. So defining these properties is actually very, very hard. They seem intuitively obvious to capture. So what we use is a proof style called non-interference, or you can think of it as the preservation of indistinguishability. Okay, so if you're not familiar with this, can I continue? Sorry? You skip this? Oh, okay. Okay, come to me later if... okay, you get the idea, right? But maybe let's stop here. Okay, so essentially what we prove for the Nitro Isolation Engine is that if you start with two indistinguishable states, two states that basically an observer cannot distinguish apart from each other, and then we invoke the same system event, for instance, invoke within the context of these two states, the same hypercall with the same parameters, or trigger a data abort or an instruction abort or whatever, then these remain indistinguishable. Now, if this property holds for every possible hypercall or system event within Nitro Isolation Engine, then we just define Nitro Isolation Engine as being kind of confidentiality preserving. Okay. All right, so very, very briefly, in terms of kind of proof coverage, we have kind of got full functional correctness and security theorems for the core VM lifecycle hypercalls that I talked about, guest-facing power management, miscellaneous utility and host management hypercalls. We've also got partial coverage for instruction and data aborts and asynchronous interrupt handlers. So there's lots of different varieties of instruction and data abort that you need to handle. We've covered some of them. And we are currently expanding the proof to cover also PCI, so devices, the GIC, so that's the generic interrupt control for ARM, expanding DNI aborts to kind of cover all cases. And as it stands, as of yesterday, the proof is about 320,000 lines of Isabelle. So this is very, very big. I think when I first gave this talk in the computer lab in Cambridge, it was like 250,000 that line. So it's gone up by 70,000 lines very, very quickly. It's expanding. So just to close, we have developed a new hypervisor from scratch in Rust. So what I want to stress is that this is in use right now. It's actually in production. You don't have to do anything to make use of it. If you were part of the Graviton5 preview, then you were already silently using this. And when Graviton5 goes GA, launches as a product, which is imminent, this will also launch as a product with it. You don't have to buy into it. You don't turn anything on in the AWS console. It's just by default an always-on feature. And our commitment to keeping customer data safe, we've formally specified and verified both the functional correctness and deep security results are the most important parts of this hypervisor. And we think that this is the first verified hypervisor to actually enter production, at least in a kind of a cloud context. And it builds on essentially two kind of unique aspects of AWS. One is kind of the deep expertise that we have in automated reasoning as via the automated reasoning group, and the fact that we also have a lot of expertise in writing virtualization software as well with EC2. And work is continuing to expand the proof. So thank you. That is me. So,
I'm sure there are lots of questions, but we might only have time for one, given that John was super quick.
Thanks, Dominic. Are you able to, so I guess you're proving that one instance can't read or write anything from written belonging to some other instance, but are you able to prove anything about the absence of like timing based side channels that some malicious person might try to use to spy on other instances?
So in a sense, the confidentiality theorems do prevent a certain class of timing side channels. So essentially they say that the implementation of the Nitro Isolation Engine never branches on any private data of a guest virtual machine instance. That is essentially the gist of them. There is, in addition to that, some engineering principles that are in play within the Nitro Isolation Engine's implementation as well. So in particular, it implements something that I think David Chisnell, who I saw earlier at the back, kind of came up with called secret freedom. And the general gist of this is that you cannot leak via like a side channel, like a speculative, like transient execution side channel, like Spectre, a secret that you just do not know. So the idea is to push out as much guest virtual machine data out of the Nitro Isolation Engine as you possibly can. Just never map it in to the virtual address space of the Nitro Isolation Engine. And therefore you just cannot leak that data. So this hasn't yet been lifted up into a kind of an invariant, this secret freedom property, but it is something that's potentially kind of expressible as an invariant, and we prove that it is in fact always secret free.
Well, okay, Chris.
Hi, impressive effort and nice talk. Thank you. I was curious, you mentioned in the beginning that, for instance, the NCC group audited the engine, right, and wrote a report. So I was actually curious to ask if they did or somebody else did the same for the proof, and how easy is to audit these proofs, right, to understand the underlying assumptions and the proving process?
Yeah, that's a very good question. That's something that we thought about. So we are in the process of contracting with a company to audit the proof and its assumptions and basically give them access in advance of the proof. So I should say that the general idea and one reason why this book has come about is because we want to reveal the source code of the Nitro Isolation Engine to our customers. So as it stands right now, we do not reveal the source code of the real Nitro hypervisor because it's got business logic tied up in it that we don't want to reveal. With this split, we will reveal it to our customers and we will reveal the proof at the same time. So it will be jointly auditable. You will be able to look at the proof, test the assumptions, also run your version of Isabelle and check that it actually checks as well. So this is one aspect. This audit is another. And yeah, there's other stuff that's going on. Like for instance, we're building LLM related infrastructure within Isabelle to allow people to query, like right click on a definition and explain this definition to me. So that's all kind of stuff that we've also open sourced as well in advance of this.